So today we're gonna learn two awesome things. One, very useful. I hope some of you take what I'm gonna show today in the first item and then um, apply to your projects. Why? Abaqus is better than us as meshing, right? So Abaqus, we're gonna learn a tool that is called automatic remeshing, right? So basically, we're gonna submit one job whose mesh is really bad, and then based on the information that we get from the first job, we're gonna remesh, and then our results are gonna be significantly improved. So that's the first thing that we're gonna do today. And the second thing is that we're gonna learn a new method. So it's like a relative cousin, sister, brother of finite element analysis. So it's more or less the same, but instead of modeling elements, we're gonna be modeling particles, right? So this method is called smooth particle hydrodynamics. It's something really advanced, it's kind of new. It's been around for a while, but now it's taking strength. And it's mostly used to model fluid structure interactions, right? So if you have a can full of water and then you drop the can, you can see this rushing, the material or the water inside the can moving, right? Waves, right? Waves are really important. So waves, how they impact your columns of a bridge. So that's how we use it. And how I have been using this method in my job is for impact, right? So last week we did an impact where a bullet just went through a plate, right? However, did we have a lot of deformation in the plate? No, the bullet just went through. This method is also used to model high deformations, like really drastic deformations. Finite element analysis cannot do it. So this method is used to model high speed deformation. So for example, there's a tutorial that if you search about this method online, you're gonna see a propeller impacting with a bird, and then how the bird damages the propeller. That's something that is seen a lot, right? How do we model the bird? Just a sphere or a cylindrical shape with some properties of meat. You can find them, right? So it's just like a, how do you say, Newtonian material? How do you say that? Yeah, Newtonian material. So you have input those properties in there, and then you see the propeller cutting through the bird. So really useful tool. How to go from an Abaqus model to a SPH model? One click, one single click. All right, extremely useful tool, right? So the first thing that we're going to do today is the automatic remeshing. So we are going to go from this plate, right, where the elements are kind of big. We see here in this region some highly distorted elements. So after I apply the load, those elements become very slender, very thin, and that is not good for good modeling practices. You want your elements to be kind of like a square. So the more refine your mesh, the less deformation that particular element is going to have. So in order to avoid those errors that are induced by big elements or elements that have the actual term is called Jacobian, that have a really high Jacobian, you go and you refine the mesh. Abaqus did this mesh automatically for me. I didn't have any special settings or anything. I just created an automatic remeshing. So we're gonna do that. And you can see here where in the regions where we are gonna have a lot of deformation, the mesh is really refined. But in these regions where we don't have anything going on, elements are quite big, right? So we are gonna do that today, all right? It's very useful for all of you, right? Because if you have this works for 3D as well. If you have a plate, if you have a bicycle frame, if you have a truck suspension thing, you just do one step, it's just running the model twice, and then you find the optimal mesh for your analysis. Okay, so let's try to do it. I'm gonna create one part. So let's call it plate. It's gonna be 2D. Deformable shell, and the approximate size is 200. Just nothing weird here. I'm just gonna create the plate. So my first initial coordinate is -50, -50, and then the final corner of my rectangle is gonna be 50, 50. All right. I'm gonna create one square here, one circle here. Let's create another circle here, and then let's create an ellipse. Okay. Random things. I don't care about what we are doing in here, just to show the tool that we are going to be using. Materials. So let's use aluminum 6061 properties. Okay, some of you are using that. So for Young's modulus, it's going to be 69 gigapascals, so 69 e to the 3, because I'm going to be working in millimeters, and Poisson's ratio is 0.3. Plasticity, so I'm going to add plasticity to the model. And for plasticity, I'm going to be using Johnson-Cook plasticity. Those properties, you can find them in literature everywhere. For steel DP590, 1040, high carbon steel, low carbon steel, magnesium, zirconium, whatever you guys want, if it's used in the industry, right? So those properties, I have them here. So let's input those into Abaqus. So material, where is it? Oh, I didn't save the changes. Okay, aluminum 6061. The elastic modulus is going to be 69 gigapascals, 69 e to the 3. Poisson's ratio is 0.3. Plasticity, I'm going to just use isotropic and then Johnson-Cook. So I'm going to enter those properties. So 324, 114, N is 0.42, M 1.34, melting temperature is 585, and transition temperature is 24 centigrade. I'm just putting the properties out there, nothing weird, all right? Okay, so I already have my material, okay? You can go ahead and take a picture. All right. Section. So I'm gonna create a homogeneous section, all right? And then I'm gonna assign that section to my plate. So I'm just gonna create a set that is called plate set. And the section for that is gonna be, oh, let me see something. Okay, I didn't create the section. Section 1, okay, homogeneous. All right, and the material is 6061, all right. And then I can select all of these and then create a set that is called plate set. And then everything should be in green. All right, so now I have the plate with my material assigned. Next thing is to bring it into the assembly. Nothing weird here. And I'm gonna apply some boundary conditions. I'm just gonna say that this bottom surface in here is gonna be fixed. So in fixing X, fixing Y, and fix the rotation. And now let's create a step. I'm just gonna create a step that is gonna be called pull. All right, and it's gonna be static and general. I don't have to move anything from here because we're not doing dynamic analysis. In dynamic analysis, here we enter the time, right, that we're going to model. In here, you just leave it as 1, all right? And then I'm gonna pull from the top. So this plate, so pull boundary condition. I'm gonna take this set in here, and then I'm gonna pull along the y direction. So all the nodes in that horizontal line, I'm just gonna pull them 10 millimeters. All right? Questions so far? Now let's go to the mesh. So for mesh, I'm just gonna go, actually, let me modify something here. I think it's more friendly if we have a white background. So for the particles, sorry, for particle node, for the initial mesh size, let's go with 5, all right? So it's kind of a coarse mesh. And I'm gonna go here and mesh the part, all right? Not our best job in meshing, right? But we're gonna let Abaqus take care of this and suggest a better mesh. I'm gonna go here to adaptivity, and I'm gonna create a remeshing strategy. This is the key part of this analysis. Where do I want the remeshing? I already created a set that is called plate set, right? So I want everything that is inside of this set to be remeshed. And here, Abaqus uses some energy computations, or some energy, computations in order to compute how accurate or how off that approximation is. So we're gonna be using element energy. And here we have some constraints. For example, this mesh, the minimum element size is 0.1. But for my design, hey, I need this to be at least or 0.5. So you can do those kind of constraints in here. For now, I'm gonna leave the defaults. And for the default, for the refinement, let's try to go to a highly refined mesh. So out of loader refinement, which is 1, and high refinement, which is 10, I'm gonna stay in 7. So our output is a very refined mesh. All right, that's it. That's the only thing that we have to do. So we're gonna create a job here. So let's create a job. Let's create a job, and let's call it plate course. Okay. And remember that my computer doesn't work, so I have to run from the command prompt. I'm just gonna go here to class material, and in the command prompt, I'm gonna go to that folder. So cd means change directory. So I'm gonna change the directory, and I'm gonna go to this directory. And then I'm gonna enter the Abaqus command. So whenever you hit submit in Abaqus, you're just typing this: Abaqus job plate course. CPUs, let's run with 16 CPUs. Interactive job, and that should be it. Let's run it. And in the meantime, I'm gonna open a new PowerPoint in here. Oh, maybe this one. So let's comparison. Let's see how the job is doing. So it's running now, and the job completed. So let's take a look at this weird plate. So the formation is kind of weird. We can go here to AC yield, and we can see where yielding is occurring, right? Here we don't have any yielding. We can also look at, for example, the plastic strain, so highly related to where yielding is. We can also look at foam misses, which is what basically says if you're under yielding or not. So that looks okay, but this is not near a circle, right? This is very far from being a circle. This ellipse is more like a banana, right? So it's very weird. So how do I improve the mesh of my current model? I go again to mesh. So let me take a picture of this. So I'm gonna copy this and paste it in here. That's gonna be my course model. Okay, this is course. This is my course job. And let's go to mesh, all right? So we are gonna go to mesh, and in adaptivity, we are gonna go to manual adaptive remesh. So for that, we are gonna open the job that we just submitted. So Abaqus is asking, hey, I need to improve the results, but give me a baseline, right? The baseline is my ODB, which is Abaqus Output Database, ODB. So I'm gonna open the job for my plate course, and let's try to see what the error Abaqus thinks is. Abaqus is giving me an error of 47%. Okay, so those results not trustable, right? Those are really bad results. Let's take a look here. Let's try to zoom in a little bit more. Let's remesh the model. So we already gave Abaqus all the constraints, all the information, the baseline for our remeshing here. So let's try to remesh. Really nice, right? So nice refinement in the regions where we have holes or where we have squares, okay? Let's run this job. So let's run plate refined 1, all right? We might run another one, okay? So I'm just gonna write input, and then I'm gonna quickly run that job. So plate refine 1. Okay, let's take a look at the results. Even for the magnitudes, our highest stress in this plate is 457, but in our previous job, it was 417. So even though that the colors look kind of similar, so let's create a screenshot of this. So the colors look very similar, but here Abaqus was saying, hey, all this region is under high stresses. It is not. It's only this region in here. In between, the stresses are not that high. However, the magnitude of the highest stress here is 457, whereas in your previous job, it was 417. Okay, so the magnitudes are wrong in our first job, and the distribution of the colors is also wrong. Let's see what Abaqus thinks the error is for this meshing. So we again go to here to mesh. For the adaptive remesh, we are gonna open the plate refined, and let's display the results. 27%. All right, so it's still kind of unrefined. So let's remesh again. There we go. Okay, so now we see some refined elements in here. So it was because Abaqus, so hey, there's a lot of deformation going in this area. We also have some high stresses in that area. You better refine it, okay? You have to run the job with a coarse mesh in order to remesh and have a really good quality looking mesh. We don't have to do this, right? If you are smart about your model and you kind of understand how your deformation works, you don't need it, okay? But if you want to say, hey, I don't want to deal with meshing at all, I want Abaqus to take care of it, use this tool, right? It's super valuable, and in 20 minutes, I've created 3 models already, right? So you can do a simple analysis, and then you show me how the error is decreasing with every mesh refinement that we do, right? So this is a cool and neat thing to add to your project if you want to get 110, right? So everything adds. If you just want to give me baseline things, I'm okay with it. But if you want to go that extra step, this is a really good thing and really good modeling practice. Let's run a final job. So plate, refine, version 2. Let's write the input and let's run it quickly. Yeah, someone had a question.
How do you open up that little menu that allows you to refine the mesh?
I'm gonna do it in a second. So for Wednesday, what's your name?
Buddy.
For Wednesday, we're proposing to submit all the projects updates online, if you're okay with that. Okay. So we don't have to meet here.
Okay.
Okay.
That works.
This is taking a while, but it should be ready now. Okay, so let's open those results. So results, let's see that mesh. Okay, our high stresses are converging. Okay, so what happens? How do I change the limits, right? Because I want to have a fair comparison against the course model, right? So the limits of the course model are 58.51. So let's change that one. So I go here to contour options. I go to limits. And here in the minimum, I'm going to add the minimum, which is, what was the minimum? 58.51. So 58.51. And then the maximum is going to be 417.9. So 417.9. Apply. Okay, and now we can have a one-to-one comparison here. So let's replace this one. And let's analyze these results. Here, we see those gray areas. So in those gray areas, the stress is higher than our actual maximum, right? So we are losing a lot of information with the first model. Also, the deformation looks kind of similar, but it's smoother in this one. I'm not applying a drastic loading here. This becomes worse as the magnitude of your loads increases. So if you have a complex contact going on and you have a weird load being applied, this becomes even worse, right? For this particular case, it's not that bad, right? But we always want to get really accurate results. How do we go again to that menu? I go here to mesh. So first error was 47%. Second error was 27%. Let's see how much it is for this one. So I'm gonna go here to mesh, adaptivity, and manual adaptive remesh. And then I'm gonna open the job that we just submitted, the plane refine number 2, and let's compute the error, 14%. All right, so what happens if I remesh again? Now it's taking a while. Okay, That I think it's an overkill now for this problem at least, right? I think that some problems do require that kind of meshing, but for this one we don't need it. All right. Cool tool that we just learned. Okay. Second thing, we're gonna model this cool process. So very similar to our previous class example where we had a projectile that was impacting and penetrating a plate. Here, we're gonna change things a little bit. My plate is gonna be rigid, right? And then this projectile, whatever you want to call it, is gonna be deformable. So what do you guys think is gonna happen after we crash? Pancake? I think it's gonna go destroyed, completely destroyed. Traditional finite element models, we cannot do it, right? Unless you have remeshing. So if your plate is deformed a lot, then you have to remesh and then keep applying the load and remesh. So it becomes very tedious, really, really tedious, even with automatic remeshing. So for those the processes, and even if you achieve it, the results are not that accurate, right? So how to overcome that? Use this method that is called smooth particle hydrodynamics, all right? It's a new tool. I think it might be useful for some of you in the future or your research. So it's a cool tool that I just wanted to show you guys. So let's model this. The modeling should be really straightforward, and then we can proceed and discuss this model, all right? Let's create a new model. Let's call SPH model. All right. So the first thing that I'm gonna do is gonna create the projectile. So it's gonna be 3D. It's gonna be solid, and I'm gonna model that using a revolution technique. The dimensions and everything is in the PowerPoint, so I'm gonna upload it after. So 3 in X, I think, I don't remember. 2.5. So 2.5 in X and 4.5 in Y. 2.5 in X and 4.5 in Y. So that's my cross section, or at least half of the cross section of my projectile. And then I'm gonna revolve it around the Z axis 360 degrees. Okay, that's gonna be our projectile, okay? For SPH, is really, really important that the mesh is kind of homogeneous and structured. So I'm gonna create a partition here in the middle that is gonna help my modeling or my meshing process. So I'm gonna go here to partition, and I'm gonna use normal to edge. So in this edge, I'm gonna partition using this edge, and basically I just split that bar in half. That improves the mesh quality a lot, all right? And this becomes kind of a standard way of doing things for this SPH modeling. That's my part. That's it. So now I'm gonna create the rigid wall. So let's call it rigid wall. It's gonna be 3D as well. It's gonna be a shell, and it's gonna be rigid, okay? That means that that won't deform under any type of loading. It just acts like a rigid material. Again, using a revolution technique. So I'm just simply gonna draw a line that goes from 0,0 to, let's say, 10,0. No. Let's say that the length of this line is 10. And that the distance from here to here is 0. Okay. Now I can revolve this, and the revolution is going to be 360 degrees. So it's simply a shell. It has no thickness. It has nothing. It just acts like a wall that it won't allow that projectile to penetrate. We have to add a rigid reference point. So I'm gonna go here to reference point, and I'm gonna create that reference point. Later on, we've done this several times. We have to create a constraint between rigid bodies and reference points. In that way, we only apply the boundary conditions to the reference points, correct? Anyone remembers that? So I'm gonna create a set that is called rigid wall, and it's basically everything but the reference point. And I'm gonna create a set that is called ref point, and I just simply click the reference point. That's all I need for now. Materials. So I'm gonna again create the aluminum 6061. So it's called aluminum alloy 6061 with thermal treatment number 6. The Young's modulus 69 gigapascals. Poisson's ratio 0.3. Plasticity. We kind of know these properties by memory. So 324, 114. What else? 114, 0.42, and 134. 0.42 and 1.34. Okay.
What if you ask for, like, does it matter if you put the reference point in the assembly versus in the part? Because it doesn't show it in the part.
Because I'm creating it from the part, but you can also do it in the. I think it's better if you do it in the part. That way, you know that the reference point is only for that part. Melting temperature 585 and transition temperature, that's only 24. We are gonna add damage, right? That way, when we have really high plastic deformation, that piece starts to break. Otherwise, I've done this at home, it's gonna bounce back, okay? It's gonna have a lot of plastic deformation, and then when the momentum is over, boom, the rigid wall rejects it. So we have to add damage using Johnson-Cook damage, and let's enter these properties. So go here. So D1, it's negative 0.77, 1.45, negative 0.47, 0, 1.6, 585, and 24. Don't trust this temperature, it's completely wrong. And I'm gonna add something that is called damage evolution. So basically, after certain criterion is achieved, then those elements are gonna be deleted, all right? So we always kind of use 0.1 for aluminum. That's in terms of the properties. I don't want to go into much detail there. That's a whole completely new work for me. So I just go to a paper and then I grab the properties out from there. I have to create my section. So I'm gonna create a homogeneous section that is gonna be referencing that 6061 property or material, and then I'm gonna assign that to my projectile. So let's call this projectile. Okay, and now everything should be green. Let's add some boundary conditions first. All right, so let's bring everything into the assembly. So I'm gonna add the projectile and the rigid wall. And just to make things a little bit cooler, I'm gonna translate this vertically just a little bit. So we see the projectile traveling a little bit and then impacting the wall. So let's move it from 0, 0, 0 to 0, 0.5, 0. So we just moved it in the vertical direction. Okay, everything looks good. So let's add first the constraint. So I'm gonna create a rigid body constraint between one body. Which body is the one that has the rigid body constraint? The plate. So I'm gonna go here to this, and I'm gonna select this set that is called rigid wall. And the reference point, I also created a set that is called rigid wall reference point. After I exit this menu, you see those blue hollow circles in there. That means that you have a constraint there. We did it using equations. You can do this doing equations. I do not recommend it. It's too weird. Okay.
Can you explain why it has to be done with respect to the reference point?
Because in that way, Abaqus knows that you apply a boundary condition to a reference point, but everything that is below, like the slave nodes, it doesn't matter, right? So all of that is just going to be rigid. So if we don't do that, it's harder to apply boundary conditions, and sometimes it creates errors, right? So it's like just being sure that everything is going to work. You don't have to create a reference point. You just could select all the nodes in the plate and then just restrict them from any movement, right? But it's a cleaner way to do things this way. All right, let's apply a predefined field that is going to be a velocity. And let's apply to the projectile. So that projectile is going to be traveling in the y-axis at a speed of 200 meters per second. All right, that's 2/3 of the speed of sound. So 0, negative 200 meters per second, so millimeters, 3 more zeros, and 0 in z. So you see that we applied that speed to that boundary condition. Sorry, to that part. And my only boundary condition in here is that I'm gonna restrict from rotation my reference point, right? And then I won't allow that to move in any of the directions. So that point is completely fixed. Fixing that point means that all the nodes in my plate are gonna be fixed as well, all right? What are we missing? What have we done differently than a traditional model? Nothing, right? So I'm gonna create a step. The step has to be static or dynamic. Dynamic, all right? So we're gonna go to dynamic, explicit. Anyone remembers the difference between explicit and implicit? Explicit is for long processes, and explicit is for short processes. So this process takes 500 milliseconds. So we should use explicit. So everything that is below 1 second of duration is better to use explicit, okay? So here, the time period is 5e to the negative 5, all right? 50 milliseconds, all right? That's the duration that I computed that this is gonna last. Now, we just go to mesh. That's the only new thing that we are gonna model in here, or vary. So let's first mesh the easy part, which is gonna be the rigid wall. And let's say that the seed size is gonna be 0.25, all right? And in my element type, which is gonna be that menu here, S4R, I'm gonna say that the element has to be explicit. That's something that you have to be careful when doing explicit analysis, all right? Who is doing explicit for the project? No one, right? You're not. Yeah, but you're applying gravity and then applying a load, but that's not dynamic. Yeah, eventually. Mm-hmm. Yeah, 10 seconds, it's better to use implicit. Mm-hmm. All right, so let's mesh. Okay, let's select the regions where the element has to be explicit, that region, okay, and let's mesh it. Okay, mesh is looking okay, and let's go to the projectile. For SPH, it always has to be yellow, all right? It's better to use yellow because that will allow to use hexahedral elements. Hexahedral is just like a brick, right? It's like a brick in 3D. It doesn't have to be that elongated. It's just a cube. But basically what we are saying to Abaqus is for each cube, you're going to replace that cube for a particle. Okay? So we are going to go here to S4R. I'm going to select everything. And I have to make sure that I'm working with explicit and hex, always hex. And in hex, we have this option in here, conversion to particles. All right, so we are going to take each element of that domain and we are going to convert it to particles. All right, for threshold, use 0. Like each element is a particle, and that's internally used to compute the spacement between particles. The particle size, it has to be the same that we use for the plates. So 0.25, that's the mesh size that we use. And then I can go ahead and mesh. All right. It's kind of homogeneous. There's some elements that could be improved, but this mesh is going to work. It's very structured along the z-axis, right? So the spacement between particles is okay. I don't going to go into much detail there. I just want to show this could be improved, but I just want to show the capability here and how this is could work. All right. Let's create a job that is going to be projectile SPH. Let's call it SPH impact. SPH impact. All right. And let's write the input file and let's run the job. So it's Abaqus job equal SPH impact. CPUs is equal to 16 and use interactive. I want to request more frames, so you can go here to field output, and instead of showing only 20 frames, I'm gonna request, let's say 50. Okay, I rewrite the input file. Yes, we already have a job file. It's okay to rewrite, yes. And let's submit the job. This is gonna take a while. Not a while, but I think in one of these computers it will take like 2 hours. How's the VDI? It's good? No? Okay, didn't run. Let's see what happened. I know what happened. I missed the density of the aluminum. So I'm gonna go here to aluminum, and in general, at the density of 2.8 e to the 9. It happened to me at home. Yeah, but I can go. Yeah. Let me show you the error. So I go to the DAT file, DAT, and I go find error. Let's see where the error is. So it's not showing here. It has to show in the message file. So let's try to search for that file. Just 1 second. Let me show you how to do it. So in the status file, here, no density has been specified for a material. In the STA, STA is a status file. So it shows how your materials, how your simulation is run. So let me run it again, and then we can see how that status file changes. So let's add this window in here, and we can see how this changes. So it's showing how it is slowly like moving. So how, yeah, let's say yes. So resubmit the job. This should have been changed already. Let's see. Okay. A deformable element references a material with 0 density, but I already added the density. Density is fine. Let's see. Properties. Here, section assignment. Yes, for the projectile. Let's write it again. SPH impact, write input. Okay. Let's create a new job. That happens sometimes, is this computer. So let's call it SPH projectile. All right. So let's write it. I'm gonna delete this job. And let's run the job in here. So I'm just gonna change the name to SPH projectile. Okay. So what happened is that I didn't update the input file correctly. That happens sometimes, I don't know why. But I just created a new job because it said that Windows, that the input file was open somewhere else, but it wasn't, so. Now it's running. So we can check here the STA file. How this is running. 1 of 50, 2 of 50, 3 of 50. So it's basically showing you what is here in the script. You don't see that, right? Because you always do right-click, submit. But this is for a developer like type of analysis. Like you want to see what's happening at every point. Because it's not always this fast. Like for some processes that I do, one of these 1 out of 50 takes 1 hour. So during that 1 hour, you can do a lot of diagnosis, okay? Okay, nice. So who wants to see how this looks like? So we are looking, right? It doesn't look like a particle to me, but if you zoom out, there's a particle in there. So let's take a look at how this projectile impacted our plate. This happened to me at home as well. I didn't add contact, right? I always forget. I don't know why. So let's add contact to the simulation, right? So I'm gonna go here to interactions. I'm gonna add general contact, all right? Always general contact. Unless you know what you're doing, but general contact is beautiful. And here I have to do a property for the contact. So I'm gonna say, I'm gonna create a property. The normal behavior, the hard contact works fine. So just hard contact between the particles. And for the tangential behavior, I'm gonna create that we have a friction coefficient between surfaces of 0.5, right? Okay. And then I select that property that I just created in there. I rewrite the input file, and then I run again, and that should work.
Do you want contact there for sliding contact?
Yes. And you can do viscous contact or static contact as well. So if you have something that is moving in a quasi-static way, so really slow, you have one type of friction. But if you have something that is moving at a really high speed, then you have a viscous or a dynamic friction coefficient. So it's running quite fast. This is a kind of a small model. Okay. So who remembers the simulations that I said that they take 2 weeks to complete? I'm running something like this, way more complicated in terms of contact. I'm creating heat, so I have frictional heat, heat dissipation, convection, and etc. But I have 10 million particles, right? Here I have only 400 particles. So it grows exponentially. It's about to finish. 45 out of 50. 46. Completed. So let's go here at the results. Let's reopen it. And now let's take a look at this beauty. Okay, doesn't make sense now, but it's gonna make sense in a second. All right. So let's go frame by frame. Everything is black because the particles, they don't have any information. They are not in contact with the plate yet. Now, contact. Stresses are growing. And it just explodes. And then there's one point where everything goes crisis, and then boom, everything flies everywhere. If you were to do this in real life, and you shoot a projectile to a rigid wall like that, after it, you don't have anything. It's just debris everywhere. So this is actually really correct of what happens to those type of analysis. But if you had more mass, less speed, you certainly will have like a spring back in here. Like you will have like under a certain point, and then it goes back. But then you can see how that behaves. You can also look at the transversal section of this. So we can go here, and then let's take a look at the transversal section in the Z-plane, and we can see the evolution of the cross section. So who is doing the Hopkinson bar test? So this is a better way to model this, right? Like for high impact bars where you are trying to characterize the properties of these materials and to get waves and things like that are going on. So this is a better way to do it. It's not always very functional, but it's really nice. You can see how it deforms. The material that was here and disappeared is that it flew really far out of the model. So Abaqus decided, I'm not gonna show it because it's not there. It's just, it flew somewhere. And then the material keeps being pushed, and then it flies everywhere. Okay.
Is there high stress in the middle?
Yeah. Before fracturing, because we are doing fracture in here as well. You guys didn't saw it, but we had cracks growing everywhere because of the damage that we added. But basically, there's no time here to form really high stresses. Like you have a lot of stress here when contact starts, but then after that it's just modeling the shattering and the fracture of this piece in here. All right, that was it. That's what I had to show. Let me stop the simulation here. I want to show you guys something nice. So let me stop the model here.